remind you maybe of your first science class you ever took, the scientific method. What the heck is that? So if you, I'm not sure where I got this from. This might have been from Wikipedia or something like that. But the scientific method is a method that has developed, over the course of human history, basically, on how you can actually answer questions about nature, right? The stuff around us. And now they organize this in this kind of circular organization. But typically what you do is you have some observation, you have some question you're trying to answer, and then you pick, what research topic you want to figure out. You have a hypothesis, you have experiments, you analyze data, and you write a conclusion about it. I'm going through this really fast because, when I was learning about this never made any sense to me. It's like, what are these things, right? The best way is for me to learn stuff is from examples, okay? And these lecture notes will be posted or already posted on Canvas, by the way, so you don't have to jog everything down. But for example, in particle physics, which is a field, one of the fields I'm in, right? Maybe one of the question is that are neutrino its own antiparticle, okay? If you don't know what a neutrino is, don't worry about it. It's just a question, right? That someone, what does that mean? Let me see how we make this text bigger, right? Okay, right? So that's a question, right? So that satisfies this first box up here, right? Okay, and so there are subset within these questions where antiparticles, just a little bit more information. Antiparticles are the same particle but just has the exact opposite electric charge, okay? Such as a proton, right, and an antiproton. A proton is actually made of two up quarks and a down quark. If you don't know what these things are, don't worry about it. There are these weird things that are particles and antiparticles of each other, right? And we see this in nature all the time. But neutrinos are actually neutral, so you cannot just measure its charge and figure out whether it's particle or antiparticle. Okay. And neutrino is also, a fermion, which is a type of particles out there that behaves like the electron, protons, and neutrons. Okay. All right. So the interesting thing is that we have detected other neutral particles that are not its own antiparticle. So for example, the neutron, right, which is neutral, so you cannot measure its electric charge and determine what type it is. But if you basically smash things into it and then break that neutron apart, you'll instead of getting one up quark and two down quark, you actually get a anti-up quark and two anti-down quark, right? And that way, now these little quarks has charges in it. Now you can measure whether it's their particles versus antiparticles. Okay. Unfortunately, we cannot do this with a neutrino because so far we have not been able to break the neutrino apart, let's say. Okay. So the research topic, right? So this is the question, right? Like what, we don't know, right? Even today, we don't know, actually. Okay. The research topic area, there's different ways to determine how to deal with this question, how to answer this question, right? So now we're in the second part of this box here, right? Okay. So the research topic, we can do astrophysics on it, meaning you use something called the cosmic neutrino background. So instead of the cosmic microwave background, you detect neutrinos from early in the universe, and you can figure out, whether or not they were made of particles versus antiparticles. And there's a Wikipedia article about this. Okay. Or you can do experimental physics, where you do this experiment called neutrinoless double beta decay, and there's a little Wikipedia article about that. And then you can figure out whether or not you're making a measurement in order to figure out how to answer this question. So this is sort of like the research topic area that's in this little box here, right? So you're going to do, so the next thing, of course, is going to be your hypothesis, right? So if you hypothesize that neutrino are its own antiparticle, right, a certain process can be observed. So you are assuming this. You have no evidence that it's true or not, but it's a good guess, right? It's one of the possible ways. So you're following, all the other physics rule, but then you're tacking on this rule that says, oh, neutrino are its own antiparticle. Okay, and so this is a neutron, two neutrons decaying into two protons. Okay, and this happens actually all the time. If you ate a banana today, this is actually happening much more inside you than the rest of us, because I didn't have a banana today. Potassium decaying. So the potassium inside a banana that some of you guys might have ate today, right, is unstable, and the neutrons inside that potassium actually decays into a proton. So this is happening all the time. You just don't realize it because it's very low activity, meaning it's not going to harm you that much when it's happening. Okay, but so that's typically one neutron turning into a proton, right? If one thing can happen, maybe two things can happen at the same time. So the chance of this happening at the same time is very low. Okay, but this process can happen, and let's not worry about exactly what these little wiggly lines and all this stuff is. But what's the important thing is that if this process could happen, you will see that, oh, two neutrons turn into two protons, and all you see is two electrons and nothing else. Okay, and this is known, and unfortunately, the name is kind of stupid also. Beta, this beta particle actually means the electron. Okay, electron and beta are the same particle name, fortunately. Okay, photon and gammas are the same, and then alpha is actually an alpha particle is actually two neutrons and two protons stuck together. How many guys did you guys do the Rutherford experiments when you did modern physics, where they figure out the structure of a atom from that, where they had a radioactive thing and then it emits alpha particles, and then they have a little the gold foil experiment. And sometimes what happened is that what people hypothesized before was that atom is just a what's called a plum pudding model, where the positive charge and the negative charge are all like kind of equally distributed amongst the entire atomic structure. And hopefully you guys know that's not true, right? There's the nucleus, and then that's positively charged, and then there's this cloud of electrons around it, right? But if you were to do the plum pudding version of it, let's do it here, right? So you have a bunch of plus charge, minus charge, plus charge, minus charge, and they're kind of everywhere, right? Right. If you were to shoot a plus 2 charge particle into it, it will most likely just kind of sail through, because it doesn't. If it was being repelled by this positive charge, it's being attracted by this negative charge, so the two forces actually cancel each other. Okay, but if you were, hopefully you guys. But our current understanding of atomic structure is that gold. I don't even know. It's like 42. There's a plus 42 amount of charge in there, and then there's negative 42 amount of charge out here, right? Kind of a cloud around it. Okay. And now if you shoot a plus 2 charge here into it, what happens is that if you get close enough to this plus 42 charge inside the middle, it's going to basically bounce straight off of it, because it's going to repel each other, right? Where most of the time it'll kind of just sail through. Okay. That's called the Rutherford scattering experiment, even though it was Morrison and Geiger who did it, but Rutherford was the boss at the time, so he gets the credit. Anyway, sorry, I think that was a little diversion. Why did I start talking about that? Oh, okay, yeah, alpha, beta, and gamma. Okay, there's also delta particles, by the way. I'm not gonna delta. You can go through all the Greek alphabets, and they all have particles named after. Anyway, so the reason this experiment is called the neutrino-less double beta decay is because double beta means you have two electrons coming out, and you see no neutrino coming out. And the idea is that if this was to happen, it's proof that the neutrino actually annihilated each other internally, so you actually don't see it. Okay, so this is the hypothesis you are guessing that neutrinos are its own antiparticle, and therefore this process is possible. If they were not its own antiparticle, this process is not possible. So you're making a guess, right? So therefore, that's the hypothesis, right? And now we have to, in order to prove an hypothesis true or not, you do an experiment. You have to do the experiment in real life. Okay. There's a couple of experiments that does this. So there's the what's called the Next InReach Xenon Observatory. It's called NEXO. The website is hosted by Lawrence Livermore National Lab, which is only about an hour from here. So they are part of this experiment. But the actual observatory is in Snow Lab. Who knows where Snow Lab is? Not you. Not Matthew, except Matthew and Jesus. Snow. Where is a lot of snow in North America? What is it? Alaska, close. But not necessarily in the same country. What's the other country that's very cold? Canada. It's in Canada. So Canada has I think it's basically a giant mine that used to be, gold mine or silver mine. I don't know what they dug out there. But now they use this as a lab, a physics lab. And the reason they put these labs underground is because they wanted to get away from what's known as cosmic rays. So being on the surface of the Earth, you are actually constantly being irradiated by the sun, by all the supernova that happens in the past. There's all kind of particle going through us right now. It's okay. That's how we evolve, actually, right? Because of these, it changes your DNA sometimes. But one of the things is that you may not know this, that by living on the surface of the Earth for like 80 years or whatever, is equivalent to taking one international flight, by the way. You basically double your dose of radiation every time you take an international flight, because the higher up in the atmosphere, there isn't the atmosphere to protect you from all these cosmic rays. Basically, it's kind of like if you were underwater, right, the sun doesn't go through the water as much, right? It mitigates the radiation from the sun. But by being on the surface of the Earth, the atmosphere actually block most of that cosmic ray. But if you are in an airplane 30 something thousand feet up in the air, you don't have that atmosphere to protect you anymore. You actually get irradiated just as much as the entire lifetime by taking an international flight for like 10 hours or whatever it is. This also happens to astronauts, by the way. Those of you who want to be astronauts. Every day you spend in space reduces like your lifetime by like a year or something like that on average. Well, something like that. I don't remember the exact number. Don't quote me. So, but it's every day you spend in space, on average you will die faster on average. Of course, there are people who live a long time, right? Astronauts are usually super fit people, but anyway, just in case for those of you, or especially those of you who want to go to Mars, Mars also don't have an atmosphere, by the way, or have this very thin atmosphere. All right, so sorry I keep going on these off discussions. But this experiment is in Snow Lab, which is about a mile underground. Okay, and what they're looking for is xenon, hence the name of this observatory called xenon. Xenon is a noble gas. What kind of lab doesn't have a periodic table? So we need to buy a periodic table for this lab. Xenon is a noble gas. And one of its isotope is 136. That means it has 136 protons and neutrons inside it, combined together. Yeah, I don't know the charge of a xenon, but you can probably look that up if we had a periodic table. But it does this. It is possible for two of the neutrons inside the xenon atom to decay into two protons. Okay, and what happened is usually, right, these two electrons comes out, but these neutrino doesn't have this self-annihilating thing. So you basically have two electron that comes out and then two neutrino that comes out, and you can measure that. Okay, and what they're looking for is they're just have this set up and just wait, and they're hoping that they will see two electrons but no neutrino coming out. Okay, and so far the decay time, those of you who know what decay time is, basically the exponential decay curve. let's see. Actually, I have the result down here, so I'm not going to quote it before I remember what it is. But the way this is set up is that you have a big vat of xenon and you just look at it for a long time. Okay, and you just collect data. By looking, I mean not with your eyes, of course. What do physics people usually look with? I'm sorry? Tools such as what detects light? What do they call?
3D printing them too.
You're 3D printing them?
They detect light.
Yeah, light sensors. Yeah, there's yeah. So I think someone mentioned phototubes. So those are photo multiplier tubes. There are also other sensors that are light sensors. So for example, your phone has a light sensor on it. Actually, this one, right? These are silicon light sensors that allows you to detect light from pictures from up here. But the light sensors in these labs are able to detect a single photon, right? If a single photon hits it, it'll actually know what it is. So if you turn on the lights here, you are looking at approximately 10 to the 20 photons per frame, meaning per like 30 milliseconds. So these sensors are 10 to the 20 times better than your eyes, basically. Okay. Anyway, but so you set up an experiment. The idea is to you have this example of, yeah, so in order to figure out if this hypothesis is true or not, you set up an experiment, right? And then once you have the experiment set up, you analyze the data, okay? And this is, some data analysis plot where they're trying to figure out how much energy is coming out of these two electrons that are coming out, okay? And if the energy is, beyond some number, that's a indication that that it was a double beta 2 electron coming out without a neutrino. Okay, and there's a low threshold, this yellow bar here. So beyond this is actually what they're looking for as signal. Okay, so this is data analysis. Okay, then I'm going to throw this in here because we're going to talk about this next week. You also have to account for all the uncertainties in your background. Okay, and this is usually like 90% of the paper is describing all these uncertainties. That's why it's so big down here, figuring out what this is. But right, the final thing in this circle up here, right? Remember, this whole thing is to do this kind of circle thing. So now we did this data analysis stuff. Now you have to report your conclusions, right? So to report your conclusion, what you do is you basically either have like what's known as internal meetings, meaning you talk amongst your collaborators to figure out, what's going on, right? Or you have these bigger collaboration meeting, or you have conference meeting, which is there's going to be one happening in March. Hopefully we can still go, where both students, researcher, professors, everyone will be showing off what the result is. For example, here, let's kind of zoom in too much, right? It's kind of an example of a poster presentation, okay? And for your presentation for this class, if you want to do an oral presentation, meaning you come up here and you do what I'm doing and you're just going through slides, or you want to do a poster presentation, both are doable, okay? And we can do like a virtual poster so it doesn't cost us money to print it. But this is what a poster look like, okay? Right, there's some pictures, there's some description and what the result is. Just some examples here. But there's also another way to kind of record your results and talk about your conclusions, right? It's by paper publication, which is what we're going to practice doing. Okay, so on this website called Archive, basically most physicists will post their the articles they write, their publication that they write on here first, because it's actually a free website. Anyone can post on here. I think there's some minimal check, make sure that it's actually a science paper. And you can actually post stuff on here if you want. So that's different ways of basically kind of reporting your conclusion. Okay, so this is the entire scientific methods. Okay, so hopefully this is not too boring, because I wanted to give specific examples. That way, this hopefully solidifies what people know about these things already. Okay. All right. How many guys seen all this already? A little bit, yeah, good. All right, but maybe not this specific example, or you guys already know about neutrinos double debated decay.
This example.
Yeah, but hopefully the methods should be the same steps, right?
Yeah.
Yeah.
I've been being spoon-fed them since middle school.
Yeah. Good. Okay. Yeah, now you should be an expert. Okay, so the next thing I want to discuss, any questions about the scientific method? The next thing I want to discuss is splashing water on my glasses. Is experiment versus theoretical. This was the question I asked when when I was your age. It's like, what's the difference between these two? And these are fictional people. So in a movie that came out like last summer, right? Oppenheimer, right? Supposedly this guy, Lawrence, what's his first name? Huh? Ernest Lawrence is the experimentalist, and then Oppenheimer is the theorist. Okay, and if you've seen the movie, they're trying to showcase that Oppenheimer is bad in the lab. He doesn't know how to do stuff in the lab, but he's a good theorist instead. Where Lawrence is a much better, he can build stuff that make it work and actually do get results out of them. Okay, and this is a divide that tends to happen more in physics than other fields, actually. So in some science fields, there's a bigger divide, and I think physics is one of the bigger ones, especially particle physics that has a huge divide between how people work if you are a theorist versus if you are a experimentalist. It's a little bit less in astronomy, even less in condensed matter. And for example, in atmospheric physics, there's really no divide. There's no theoretical atmospheric science physicist, and there's no experimental atmospheric scientists. They're just atmospheric physicists. That's it. So let me just show you kind of another example, right? Just to differentiate the two. Okay. So let's say someone has an observation, right, to figure out the effects of the traffic pattern in Austin, Texas, how it affects the nitroxide vertical distribution. So this is a science question also, right? What they observe is that there may be the hypothesis is that the daily cycle of either morning or evening traffic, so people tend to drive to work in the morning, drive home in the evening, and then nothing in the middle, right? Can cause an increase of this particular gas, nitroxide, as NO3 concentration to basically build up and basically flow upward into the troposphere. Troposphere is the layer of atmosphere that we live in. So hopefully you know where that is. Okay. So if someone asks you where do you live, say the troposphere. Okay. Sorry. Okay. So the experimental method is a lot of times you actually it's really hard to build up a lot of data. So but you can obtain the data itself using either ground-based instruments, so you can build an instrument, measure it, or you can build a satellite and then launch it into space and cost $1 billion and measure this vertical distribution of nitroxide in Austin, Texas, right? This is just an example. Okay. And you want to measure this multiple times at different time of the day. And then the data analysis is going to be, oh, well, what's the vertical distribution? Okay. And then, and then you have a conclusion about it. Okay. This is one person doing all of these steps, right? So this person, right? So let's go through this, right? So this first step is what again? Remember? The observation of the question, right? Okay. This second step is the hypothesis, right? And then this third step is someone else from this side. The what? So what's after hypothesis? Sorry? Yeah, well, yeah, the experiment or analyzing the data, right? Okay. This fourth step is actually the data analysis, right? Okay. And then of course you write a conclusion and you report your results. Okay. And this is actually sort of an interesting result for this particular area, but we don't have to go through the actual science itself. But like one person or one group of scientists does all of these steps. They do the entire scientific method. Okay. More extreme example, on the other end, where these are divided, okay, is in particle physics. So what a theoretical particle physics would do, this is just me making up a question that someone might ask, right, about dark matter. So the question that theoretical physicists will ask, that's the question, right? What is the makeup of dark matter beyond what experiment can exclude so far? Okay, so what are the possibilities? So this particular scientist, right, will come up with a new possible interaction of dark matter that's created, where the dark matter is created in the early universe. Okay, what this person will do, right, will do either pen and pencil model, or even more likely computer model these days, to basically determine how this interaction will actually cause the distribution of dark matter change, right? Some sort of signature that they would hypothesize will happen, right, in this model, okay? And then publish this information without doing the experiment, right? So what was this again? The first step?
Observation.
Observation or question, right? And then this is sort of like, the two are a little bit squishy, but this could be considered like the field of research, like, oh, what possible interaction, right? And then running the model, right? This is not an experiment, right? This is like a what again? Hypothesis, or more succinctly, a guess, right? A guess that this could happen, right? And then you assume this. Okay. And then you skip the experiment and the data and the actual data analysis, and you publish, right? This is what happened in theoretical particle physics. Okay. But it works well because due to the fact that the skill sets are a little bit orthogonal between them, is that what an experimentalist would do, an experimental particle physicist would do, right, is basically read this paper, okay, and then, oh, there's this new model of dark matter, and now, right, you start with a hypothesis instead of the question, okay, and then you look for, oh, well, what kind of signal could be detected, with either the current detectors or the ones you want to build, right? And then you actually conduct the experiment itself, hence the name experimental, right? And you actually, either build the experiment or even look for data in the current experiments already, and see if you can see this new model of dark matter in the data, right? Right, and then you do all the data analysis stuff and all the uncertainty that's going to take you like a year to do, and then you publish your results. So you see that in this particular field, the scientific method is applied, right, same as the atmospheric guys or ladies, right? But then it's done by different groups of people, right? Where you can just have this kind of cutoff point here, right? And then the experimentalist does the rest, right? So hopefully this is useful when people are, especially those of you who are keen on going into academic research, is that there is a separation between in different pieces of the scientific method, and depending on which field of physics you go into, or science, doesn't have to be physics, you get to do more or less of each piece. Okay. All right, any questions? I think hopefully I'm going to talk 10-15 minutes about documenting your work, which is going to lead us to what we're going to do on Monday. Any questions about, because I had this question and no one could give me an answer when I was your age. Sorry, I'm scrolling a lot to go back to where this is. Yeah. How many of you guys have either have a extreme preference to experiment or extreme preference to theory, or you prefer a field that can do both? Let's do experiments first. Who has a strong preference of only doing experiments? Okay. Who has an extreme preference towards only doing theoretical work? And it doesn't have to be academic. If you're doing private industry work, there's still theorists who does that, right? Yeah. So, one. Who wants to do a type of science where you can do everything? Okay, good. Yeah. Yeah. And, I'm not saying, one is better than the other or anything like that. It's just the way that things evolve over time into this type of situation. Okay. Okay. Documenting your work. And this is where we're going to lead into the first assignment you're going to be doing. I don't know why I jumped away. Is it jumping? How is this possible? This. I'm going to use the scroller and also turn off my touchpad. Okay. All right, documenting your work. Okay, so this is something that when I took this class, my professor told me that, if you came into the lab, did a bunch of stuff in the lab, and didn't write anything down, you didn't do any work that day. Okay, so unless you can document what you're doing, you literally have not done your work. Okay, so and this is a famous physicist, and I'm not going to be able to pronounce her first two name, but Dr. Wu, right? Well, she's discovered basically the weak interaction, which is one of the four fundamental forces in the universe. But unfortunately, at the time, this was in the 1950s, so women did not get a lot of credit for doing physics. But this is a photo of, the reason I put this is because she's writing something down, okay? So when you're doing stuff in the lab, right, you should always have some sort of documenting ability. And in this class, what I'm going to do is teach you guys how to do it on a computer, right? In other places, like what Cecilia is doing right now is writing things down, right? And Jonathan is doing, everyone's writing things down, right? So don't just do this in the class, do this in the lab also, okay? Okay. So in the experiment physics class, sometimes it's called advanced physics labs, right? We are trying to build up your experimental skills. So, we're going to, not do the, start with the hypothesis stuff and then try to conduct the experiment, analyze data, and write the conclusion. Okay, it's the latter half of that clock, right? So we're going to show you how to set up an experiment yourself, just using equipment and manuals and data sheets and the internet, right? And how to collect data and how to interpret the data itself, okay? And how to do background research on your results and document them in a notebook in a lab. And this is what we're going to talk about coming up, because it just matches with what we're going to do on Monday. And also document your work in scientific writing, which is what we're going to do hopefully by the end of next week. Sorry, beginning of week 3. I'm going to teach you guys how to use LaTeX in order to basically document what you have written down. And also be able to do peer review and also reflect and improve your current, improve the current understanding and how to do conclusion writing, okay? So the first thing we need to do is to get you guys using actually this as your notebook. So despite the little glitch on jumping around, this is actually running on what's known as Jupyter Notebook already. So those of you who have the data science class already more familiar with this interface. But if you haven't, this entire lecture was written using Jupyter Notebook. In case people didn't notice the sign up here. And first of all, you think, wait, isn't this a Python thing? Shouldn't this be about coding? But this doesn't look like code, right? This looks like English. Hopefully, it looks like English. This particular subset, this what was this called? This package inside Python allows you to run this thing called Jupyter Notebook, which basically kind of combines kind of note-taking, documentation, but at the same time you're doing coding. And that's why this particular setup is ideal for this class, because what's going to happen is that you're going to be in the lab, you're going to be setting up your experiment, as I mentioned, right? As you're setting up experiment, you can type in your notebook here what you're doing, okay? And then when you collect the data, you can put that data onto the notebook and then plot it right away, okay? And this is actually, if I'm doing data analysis on smaller data sets, this is actually how I work even today, okay, using Jupyter Notebook. When I need to do something that's much bigger, then I can't use this because it just crashes the laptop. But this is a good way to work on small data sets, okay? So this class, right, the entire point of Notebook, you can either be a physical one, a digital one, you can use OneNote, Google Docs, or even Microsoft Word, just anything that can write, right? You want to write down and document exactly everything you did in the lab, okay? And that's also one nice thing about digital notebooks. You don't have to worry about like how many pages of notes you're taking up. And then now if I have, 10 notebooks, I have to carry that around and stuff like that. But some places they may require you to have a paper notebook. Anyone want to venture a guess why they, let's say a corporation wants you to not have a digital notebook? Yes. I'm sorry? Yeah, because digital stuff are much easier to copy. Do you have Robert? Do you have another? Yeah. So what happened is that if you were to work in certain company, I'm not going to name who, like Nvidia, right? Right. When you're working on some of their hardware, you literally cannot take any information outside their lab. And when you leave the lab, they literally just take your notebook and they put it in the safe, right? Because they are paying for that. That's the important thing to them, is that knowledge, right? Their fabrication, system may be worth, $1 billion or whatever, right? But the technology of the knowledge on how to build that and how to run that and how to improve that in the future is worth 100 times that, right? So knowing how to keep a notebook, whatever format it is in, wherever you end up working, you have to follow what they tell you to do. And so in this class, I'm going to tell you to use Jupyter Notebook because, right, as I mentioned, you're going to be taking notes as you do the lab, okay? And you're writing down the steps you're doing, okay? And then the data will come out, and these are going to be small data set compared to what, in a lot of places, what real life will be, okay? You can paste that into your notebook, and then you can just do the data analysis right there in front of you, okay? Small data set, this works very well, okay? Right? And we're using this thing called a markdown function. So in case you haven't noticed, so this is not Python code, right? This is actually if I double click, so this is what's known as markdown code encoding. And this markdown coding is kind of like a combination of hypertext markdown language and LaTeX. This is its own separate thing. It's like, yeah, but it works. Oops, let's not do that yet. Okay. And in order to do this, both the markdown and the Python code all in one place, which is nice, right? So you don't have to have two separate, program in order to do this, take the notes and then run your Python somewhere else, right? You need to install something that will support Jupyter Notebook. And so those of you who already knows how to, deal with your own Python distribution, these are the packages that you need in order to do everything in this class. There may be more stuff if you want. If you want to do like machine learning stuff, you can install Scikit, but it's not required, right? But I know most of you may not have dealt with Python before. So what we're going to do is just have you guys install this thing called a package manager called Anaconda. Okay, and for whatever reason, this picture is really big. Okay, I should have made it small. Okay, so Anaconda is a package manager. What the heck is a package manager? So Python is kind of like the base language that you can build a lot of stuff on. And packages are stuff you put on top of Python in order to do certain things. For example, this Jupyter Notebook thing is a package on top of Python so that it runs the Python code and it translates it into some sort of graphical image that's compatible with HTML, the hypertext markdown language, and then it can display that on your browser, right? That's a package on top of it. The other packages you need is the numerical Python and scientific Python. The notebook thing is the notebook thing. And you also need to make plots. So there's this package called matplotlib in order for you to, and IPython kernel, those are the interactive kernels. That way you can run things in real life, real time, sorry, not real life. Okay. There's more description of what Anaconda is and how it makes money and why do they offer these. So this package is, this program is free, as long as you don't ask them for support. So basically, they make money off the technical support they offer to companies. Okay. And there's information on how to download it. I think I'm going to make this into an assignment on Canvas, and therefore you can do it on your own time. But before class on Monday, 5 days from now, right? What I want you guys to do is basically have this Anaconda installed. This will be an assignment that I put on Canvas, by the way. All right, where you're able to at least run this hello Python, and I think actually I'm going to have you do something else just to make sure that you have the right packages. Maybe I'll have you make a plot and print some numbers out or something like that. That's just to make sure that everyone has the right packages, so we're not missing anything. Okay. So for Monday, make sure if you have your computer, bring your computer next Monday, because we're going to be going through these code yourself. And it's going to be super boring if you just sit there and listen. Okay, you don't get to do it yourself, right? And if you don't have a computer that you can bring to class, let me know. We can try to figure something else out. Okay. And I think that's it. So